Hello everyone, this is Vaibhav Pandey and this is my research elevator pitch. So a quick introduction about myself. I'm a 5th year graduate student at the University of Utah and my thesis advisor is Anurag Singh. I like to think about invariant theory, local cohomology modules, D modules, and affine semigroup rings. Especially my research has been focused on how homological properties of rings could vary depending on the characteristic by using these tools. What I want to talk about today is a couple of projects that I have been involved in. The first project is regarding cohomological dimension of Veronese ideals. Now, once you have an ideal, there may be several notions of its size. A geometric notion of the size of an ideal is its height, while a homological notion of the size of the ideal is its cohomological dimension, which is just the top non-vanishing of the local cohomology module supported at that ideal. What we show in this project is that for Veronese ideals, that is for ideals defining Veronese subrings of polynomial rings, these two notions of size are exactly the same. Now this result was, and that is true over any commutative Noetherian ring. Now this result was known over fields of characteristic 0 by a result of Ogus and fields of positive characteristic by a result of Peskin and Spiro. So our result applies, for example, for the Veronese subrings of a polynomial ring over the integers. The key tool to achieving this is by looking at the local cohomology modules supported at the Veronese ideal as a D module. What we do is we analyze the kernel of the multiplication by P map as a D module and then exploit the fact that we are sitting in mixed characteristic so that we can get to use D module techniques both from characteristic 0 and characteristic P to analyze the kernel of the critical local cohomology modules. A second project that I have been working on concerns the singularities of the pinched Veronese rings. This is joint with Kyle Maddox. What are pinched Veronese rings? Now, a pinched Veronese ring is simply a ring obtained on removing any algebra generator of a given Veronese ring of a polynomial ring. So here is a quick example. This ring, K joined x4, x cube, y, xy cube, y4, is obtained by removing the algebra generator x square, y square from the fourth Veronese ring of the polynomial ring in two variables. Right? Now, these pinched Veronese rings have been objects of interest in the past few decades. The causalness of some of these pinched Veronese rings has been difficult to prove and has been an active area of interest. What we do in our project is two things. We first determine precisely when is it that these pinched Veronese rings are Cohen-Macaulay, Gorenstein, and complete intersections. Secondly, when the characteristic of the underlying field is positive, we show that these rings interestingly display a variety of F singularity classes. That is, depending on the generator that you pinch out of the Veronese ring, these pinched Veronese rings would be F regular, F injective, or F nilpotent. F nilpotent singularities are new in the literature and in principle are opposite to F injective singularities, and not many examples of these singularity types are known, and we hope to provide a bunch of examples through this project. A third project that I am working on concerns this question: are determinantal rings direct summands of polynomial rings? Let's try to understand this question, and I'll talk more about this in my jam talk. This is joint work with Mel Hoxter, Jack Jeffries, and Anurag Singh. So take X to be a m by n matrix of indeterminants and consider its determinantal ideal, that is its ideal generated by the size t plus 1 minors of the matrix X in the polynomial ring K adjoint X. The corresponding quotient ring, that is quotient by the determinantal ideal, is what is called a generic determinantal ring. It turns out that these generic determinantal rings are fixed subrings of the action of a group on a polynomial ring. So over an infinite field, these generic determinantal rings are the fixed subrings of the action of the general linear group GLTK on a polynomial ring. How exactly this action works is something we'll talk about in the jam talk. But at least in characteristic 0, since the general linear group is linearly reductive, it follows that the determinantal ring splits from a polynomial ring. That is the polynomial ring inside which it naturally embeds. What we determine in this project is if the inclusion of the determinantal ring inside the polynomial ring in which it naturally sits, if that inclusion splits or not. We'll see in the talk that a positive or a negative answer to this question both shed more light on our understanding of F regular rings. Thank you so much, and I'll see you in the talk.